Assalamualaikum. My name is Rabiatul Arwah binti Mazmi, TB21066, and I'm from Group 3, and we're going to present our project is Hooke's Law.
Assalamualaikum and good afternoon to the lecturer. My name is Toha Sinam Sulaiman and my matric card number is TB21048.
Assalamualaikum. My name is Nur Fatin Amira binti Airus Shahidin, TB21055. Today I'm going to present about the objective, introduction, theory, apparatus, and the graph of our experiment, which is the Hooke's law. The objective of our experiment is to test Hooke's law. Hooke's law asserts that the amount of stress applied to an elastic material causes it to change size and form in a direct proportion to the amount of stress applied. For the introduction, Hooke's law is a law of physics that states that the force needed to extend or compress a spring by some distance scales linearly concerning that distance, that is, Fs equal Kx, where K is a constant factor characteristic of the spring. In many other circumstances where an elastic body is deformed, such as when blowing on a tall building or a musician plucking a guitar string, Hooke's equation holds to some extent. A linear elasticity of Hookean body or substance is one for which the equation can be assumed. Hooke's law is only a first-order linear approximation to the real response of springs that other elastic bodies to apply force. It must eventually fail once the force exceeds some limit, since no material can be compressed beyond a certain minimum size or stretched beyond a maximum size without some permanent deformation or change of state. Many materials will noticeably deviate from Hooke's law well before those elastic limits are reached. However, as long as the force and deformations are small enough, Hooke's law is an accurate approximation for most solid bodies. As a result, Hooke's law is widely applied in sectors of research and engineering, and it serves as the foundation for numerous fields such as seismology, molecular mechanics, and acoustics. The spring scale, manometer, galvanometer, and mechanical clock balance wheel are all based on this idea. For the theory, the behavior of an ideal spring is described by Hooke's law, and it is a system in which a generated force is linearly dependent on how far it is stretched. A force equal to kdx is required to extend a spring by an amount of dx from its previous position. The spring constant k represents the quality of a spring. To prove Hooke's law, you must prove that the force and the distance at which the spring is extended are proportional to one another, that is linearly dependent on one another, and the proportionality constant is k. This is the apparatus that we need for our experiment, which is rollers, spring, rubber band, thread, weight calibrations, hook, and tape. Figure 1.0 shows the apparatus of Hooke's law experiment using spring, while Figure 2.0 shows the apparatus of Hooke's law experiment using a rubber band. Figure 3.0 shows the graph of stretch in cm and the force in Newton using spring.
Now we'll proceed with the procedure. First step is we need to set up all the apparatus of this experiment by placing the hook as it will be used to hold the spring. Then we will place the helical spring onto the hook. The second step is to place a ruler vertically alongside the helical spring, as it will be used for measuring the elongation of the spring when weight being placed. Third step, we need to measure and record the initial length of this helical spring. So we obtain 2.5 centimeter of the spring of length. Safety tip: before measuring the elongation of the helical spring, make sure to start recording the measurement at the same spot, and the eye's position should be the same level or perpendicular with the mark. So you need to measure it like this. Another precaution when data being taken from the measurement is by using another ruler used to point the exact length of the spring extent when weight being placed to it. The data that been recorded during the experiment are by measuring the elongation of the spring when each weight being placed during the experiment. Okay, step 4. We need to attach this 50 gram of weight to the hook of the spring. And then we will record the spring extent. From here we can say that the spring extend to 3 centimeters, so it extends for 0.5 centimeter when 50 gram of weight being placed. Then we unload the weight. Then this step 4 will be repeated for all of these other set of weight. For all the steps on taking the measurement for each weight will be shown in this video. Now we will proceed with 60 gram of weight to the hook of the spring. Now we can proceed on taking the data. The spring extends to 3.5 centimeter. Now we remove the weight. Now we will proceed with 70 gram of it. So we attach it to the hook. Okay, now we can see that the spring extends to 4 centimeters. And now we remove the weight and proceed with 80. Now we will attach this 80 gram of weight to the hook of the spring. Then we will record the spring elongation. So from here we can see that the spring extends to 4.5 centimeter. The spring extends. Then we remove this weight. Now for 90 gram of weight. Now we attach this weight to the hook. Now we record the spring elongation. So from here we can see that it extends to 5 centimeter when 90 gram of weight being put. And now we unload the weight. So now we will proceed with 100 gram of weight. So we put the weight to the hook of the spring. Now we measure. So from here we can see that it extends to 5.5 centimeter when 100 gram of weight being put onto the spring. Now we unload the weight and we proceed with 200 gram of weight. Now for 200 of weight, we can see that it extends. The spring extends until 10.5 centimeter. And now we remove the weight. Proceed with 300 grams. And we put onto the spring. So for 300 grams of weight, we obtain the spring extend until 15.5 centimeter. Okay, we remove the weight. And now we proceed with 400 grams of weight. So we will attach or hook this weight. Now we proceed with 400 grams of weight. So from here we can see that the spring extends to 20.5 centimeter. And now we unload. Now we remove the weight from the spring. So lastly, we put 500 grams of weight onto the hook of the spring. So from here we can see that the spring extends until 25 centimeter. And then we remove the spring. Now the procedure is being repeated on a rubber band. The rubber band initial length is 4 centimeter. For 50 grams, the rubber band extends until 6 centimeter. For 60 grams, the rubber band will elastic until 6.5 centimeter. For 17 grams, the rubber band will elastic until 6.5. Rubber band will elastic until 7.5 centimeter. For 100 grams, the rubber stretch until 8 centimeter. Next, for 200 grams, the rubber band elastic until 10 centimeter. For 300 grams, the rubber band stretch until 15 centimeter. For 400 grams, the rubber band will elastic until 20 centimeter. And for 500 grams, the rubber band will elastic until 23.5 centimeter. Then we record all the mass and the elongation of the spring into the table.
So from here, I will present to you the observation, discussion, and conclusion. So right now for observation, based on our observation after doing this experiment, we get to conclude that if the mass increases, the force also increases. The increase in force can cause the spring to stretch until their maximum capacity. So as you can see here on the graph, the force that the spring applied to is linear or proportional to the value of the stretch. Not only that, if the force increases, the elastic potential energy also increases. Next is discussion. From this experiment, we can conclude that this experiment have achieved the objective, that is to put Hooke's law to the test. According to Hooke's law, the amount of stress applied to an elastic material causes it to change size and form in a direct proportion to the amount of stress applied. From the table on the right here, we can see that the increased number of mass here can cause the changes in the stretch of the spring or rubber band that is used. So how does this happen? So based on the theory given, to extend a spring by an amount of dx from its original position, a force F equal to kdx is required. The quality of each spring is represented by the spring constant K. So this is spring constant K formula. K equal to F divided by E. Next, to establish Hooke's law, you must show that the force F here is linear to the length of the spring stretch. So as you can see here, the force and the length of the stretch is linear to each other. So as you can see from the table right here, we can conclude that this experiment has proven the theory behind Hooke's law. Okay, last but not least, conclusion. The purpose of this experiment is to investigate the relationship between the stretch of the spring and rubber band with the force that implies into it. The result shows that the stretch of the spring increases with the amount of force implied into it. As I showed in the graph above, the average for the stretch of the spring was 0.518 meter, while the average for the forces that implied into the spring was 13.72 Newton. The hypothesis that the spring will stretch according to the force applied into it was supported. That's all from me. Thank you.